Alright, in this video we look at more complicated regions and different coordinate systems. And so let's begin with this region right here. We'll call this region 1. One way that this problem can be made more difficult, for example, is if, and it's good practice to try this on a simpler problem, is that if we were asked to find the area of this region, we would need to integrate over region 1 dA. We could try to find the area of this region in a variety of different ways. One way would be to do it geometrically, and so we already probably know the answer here. The area of this region is, there's two triangles, so it'd be 1/2 the base times the height. So the area of that triangular region there would be 1/2 the base, which is 1, 1/2 the base, which is 1, the height, which is 1, and then there are two of those regions, so we'll multiply by 2. So I think we can see here that the area of that whole triangle should be equal to 1. Okay, so that's the answer we're looking for. Okay, if you're asked to do this, set up this integral, set up the area integral in polar coordinates. This is not an obvious choice, but it's good practice for problems where polar coordinates is the way out. This region is a triangular region. There is nothing circular about it, and so polar coordinates is always going to be a slightly non-obvious way to go. So if we remind ourselves about what polar coordinates is, x is equal to r cosine theta, and y is equal to r sine theta. All right, so what we are seeing here, excuse me, is that we have the region which the top line of this region is y is equal to 1. So if y is equal to 1, we can find an alternate formulation of that if y is equal to 1, then 1 will be equal to r cosine of theta, which means that r is equal to 1 over cosine of theta, which is also called the, let me see, this should be sine of theta. I think I said that, or this is sine of theta, this is sine of theta, and then we will have 1 over sine of theta is also called the cosecant of theta. All right, so if we're trying to set up this region of integration, what we can see is that, and we were trying to set this problem up in polar coordinates, we would integrate 1 again, like always, and then we'd have the r dr d theta, as we always do for dA. But then we'd have to set up the limits of integration. And the radius we could see, we would have these circles, okay, getting bigger and bigger and bigger, okay. Right, there we have these circles. But we need to exclude quite a bit, right? We need to exclude these parts of the regions and focus only on the part that is inside of the triangle. So what we're seeing is that the radius depends on the angle theta, right? If we're looking at this point here in the region, that point is on a circle of radius 1. But this part of the region, can we see, we needed to have our circles get to be bigger radius, right? So this point here of the region is on a bigger circle, bigger than 1. Okay, so what we're seeing is that any point in this region is on some circle of some radius. So the radius, has to go from 0 up to r is equal to something that we have yet to determine. But we can see from here, right, that we have an interesting formula that r is equal to the cosecant of theta, right? Which says that any point on this line, y is equal to 1, any point on y is equal to 1, this is the polar coordinates description, polar coordinates version of the line y is equal to 1. The radius is cosecant of theta. Okay. Now what we don't know, right, is how far theta extends. Okay, theta extends from where to where. Now we know that theta is measured from the positive x-axis up, right? So theta, we can't start at 0 because that's in the exclusion zone right here. So we need to go from theta from somewhere, this value of theta right here, up to and around all the way over to here. Okay, so theta will be, let's see if we can figure out what this is going to be, and then we can double check it. Right? If you notice this triangle right here, you can see the triangle that was formed. Here's the exclusion zone. Right? But we can see from that exclusion zone that there's a triangle that's made with base 1 and height 1. Right? And so we're looking for this angle theta. Right? And from there, from this triangle, we can see that another way of a trig identity that comes out of that triangle is that the tangent of theta is the opposite over the adjacent. So the tangent of theta is equal to 1, which implies that theta is equal to the inverse tangent of 1. The inverse tangent of 1 is equal to pi over 4. Okay? So you'll notice that when tangent is equal to, when the theta is equal to pi over 4, then the radius when theta is equal to pi over 4 is equal to the cosecant of pi over 4, which is 1 over the sine of pi over 4, that we get 1 over square root of 2 over 2, which is equal to 2 over square root of 2. So this point right here, when theta is equal to pi over 4, the radius of the circle that that point is on, okay, is on a circle of radius 2 divided by the square root of 2. And the point being here that we now know that theta goes from pi over 4, and then it extends, theta goes from pi over 4, and it extends from pi over 4 up to pi over 2, and then up to 3 pi over 4. So this region right there is from theta is equal to pi over 4 up to theta is equal to 3 pi over 4. Okay? So if we were to compute this integral, okay, that we have just set up, we should get the answer 1, because this double integral is the polar coordinates version of that triangular region there. So let's double check and make sure we've got the right answer. Let's do our writing assistant in Mathematica. Okay, let's set up our double integral. And now I know while I'm typing this that you're thinking this was just a terrible choice of coordinate system for this problem. Why do we make it so difficult? And I agree that polar coordinates was not the way I would have gone with this problem had we not been asked to do it. So we will see that there are times when choosing polar coordinates, even though the region is hard, it might be the only way to go on a problem. So here we have the radius going from 0 up to cosecant of theta. So here we have what we mean by a non-standard or a harder region of integration, in that our limits of integration in the polar coordinates r theta are no longer constants. Okay, so let's hope that we get 1 for this answer, and we do get equal to 1. Okay, so in the next video we're going to look at polar coordinates And we're going to try to find the volume of this little region right here, which is kind of like a little slice of the circle. So it's not the full circle, but a little front, like the cornea part of an eyeball, for example. So what is the area of that region? And we'll use some of the same skills that we used in this triangular region. So more on that in the next video.